This is part 3 of my frequently asked questions for week 1. One of you said I still need to work on getting Q parallel, the parallel component of Q, and remembering the formula to find the parallel component. And several of you asked questions like this, so I wanted to do one of these and really go into detail on how the formula works and why it works geometrically, because I want to give you the message that if you don't remember the formula, one way to figure it out is to just write some things down and start doing geometry. So I'm going to draw a picture of two vectors. This vector will be called v. Let's make that bigger. And this vector will be called u. U is a unit vector. I'm giving that as part of the problem. A unit vector. The reason I'm making u a unit vector is because the formula given in the book assumes that you're projecting onto something that is a unit vector, or you're finding the component of v parallel to a unit vector. So I'm going to assume that here, and then talk about what you might do if this isn't a unit vector. Okay, the idea of a projection, or of a parallel component, is I'm basically trying to figure out how much of this vector goes in this direction, and how much of it goes in a direction perpendicular to this vector. So what I'm really doing is I'm trying to figure out what this vector is, not just the length of it, but what this actual vector is, and what this vector is. This video is going to focus on finding this component here, the one that goes in the direction of u. You'll notice that I've taken v and acted as though there's a light shining from directly above the vector u, and looked at what the shadow of v would be on the vector u. Okay, now question, how long is that shadow anyway? Well, in order to find the length of the shadow, I know that this is a right triangle, so I can try using trigonometry. I know that I have some angle here. Let's call it theta. I'm not exactly sure what theta is, but I'm hoping that I'll be able to figure it out in a little bit, or at least use that information somehow when making the calculation. Okay, well, the length of this blue vector, which is v parallel, that one there, that's v parallel. The length of v parallel is going to be the length of v times the cosine of that angle, because I'm finding the side, the leg of the triangle adjacent to theta. So it's v cosine theta. Now at this point I'm going to step back here and say, just a minute now, this looks like something that I've seen before. This looks an awful lot like that formula, that geometric formula for the dot product of v and u. The only thing that is missing is the magnitude of u. But the magnitude of u is 1, because u is a unit vector by definition. So there's no harm in me going ahead and saying, this is not just magnitude of v times cosine theta, this is actually magnitude of v times magnitude of u. Times cosine theta. Okay? Adding this to the formula or multiplying this doesn't matter because the magnitude of this vector is 1. Now that's exactly equal to v dot product u by the geometric formula for dot product. Now let's think about that. That means that the length of this blue vector is equal to v dot u. Okay, that doesn't tell me what the vector is though. In order to find what the vector is, I need to think and realize this vector goes in the same direction as u, it's just a different length. Okay, I have u going in this direction, and its length is 1. Okay, if I have a vector of length 1, and I want to make it have a different length, the length is the v dot product of v and u, that means I just need to take my unit vector and multiply it by whatever the magnitude needs to be. That's v dot w. So my parallel component is going to be my unit vector times the magnitude that I want it to have, which is v dot u. And that's the formula that I get. That should look familiar to you. The dot product of v with u times u, where u is assumed to be a unit vector. Now that assumption that u is a unit vector is important because I could very well ask you a question where you have to project v onto something that isn't a unit vector. What do we do then? So let's say we want to project V onto W, and W is not necessarily a unit vector. I think that the way most of you would handle that situation is you would turn W, the direction you want, into a unit vector, and then use the projection formula on that, and that's a good way to go. So we let U be equal to the vector W divided by its own magnitude. That gives me a vector in the same direction as W, but now with unit magnitude, and then I use the projection formula. So V parallel is equal to V dot U multiplied by U. But U is equal to W over the magnitude of W, so this is equal to V dot W over magnitude of W times W over magnitude of W. But now that can be simplified to V, let me try that again, V dot W over the magnitude of W squared times W. And that's where the formula that some of you saw yesterday came from. V dot W over the magnitude of W squared times W. And this formula will work even if we don't assume that anything here is a unit vector. So you may find it nicer simply to use this formula when asked to do a projection. This way you don't have to worry about whether the thing you're projecting onto is a unit vector or not. But be mindful of whichever formula you're using, be mindful of what the assumptions are. In this case, we assume this, both instances, is a unit vector. Here, we don't make any assumptions about W at all, really, as long as it's not 0. Okay, there will be one more video about doing airplane problems because there are many requests for that, so stay tuned.